For video 2 of topic 14, we're going to look at different ways that we can analyze a quadratic height model. So the idea behind a quadratic height model is simply this. If we have a situation where an object is projected straight upwards, so let's say we have a person standing here with a ball and they flick that ball straight up so that there's no horizontal component to the motion. And so such that, say, the ball reaches some maximum height and then falls directly back down into their hand. This motion, or this height, the height that the ball achieves when it's tossed, can be modeled using a quadratic function. The quadratic function that we use to model it is a model that ignores air resistance. You need calculus to be able to deal with air resistance, so we usually start with a simplifying assumption that we do not have air resistance, which at low velocities is an okay thing to assume. So the model is height as a function of time is equal to 1/2 the acceleration of the object, and the acceleration is typically going to be the acceleration due to gravity, and this is going to be times time squared plus v naught times time, and v naught represents the initial velocity or initial speed of the ball or the object that's being launched. So the initial speed, the speed at which it's thrown, acceleration due to gravity, plus h naught. And h naught's going to be the initial height, or the height from which the object is launched, thrown, tossed. Acceleration due to gravity, there's two typical measures that you will run into in your science classes. So acceleration is either going to equal -32, and this is going to be measured in feet per second squared. This is if you're in the English system of measurement. If you're working in the metric system of measurement, you're going to have acceleration usually equaling -9.8 meters per second squared. And then what we do is we multiply that acceleration by 1/2. So if we take the -32 and we have it, we get -16. And if we take the -9.8 and have it, from multiplying by 1/2 up here, we get -4.9. And again, these numbers are negative. These numbers are negative. These accelerations are negative because we're assigning down as negative and up as positive. And acceleration is towards the ground or in the negative direction. It's a thing that pulls you back down to earth. So a typical height model might, when it's set up, might look like this. Height as a function of time equals -16 from taking 1/2 the acceleration times the square of time plus, let's say, 30t plus 12. And we would interpret this as, here's half the acceleration due to gravity. This is the initial velocity. We're measuring, this number is being measured in feet per second squared. So this number's a velocity or speed in feet per second. And this 12 would represent 12 feet, or the initial height of the ball. A metric setup might look like this. Height as a function of time equals, now we're going to use the -4.9 coming from the metric measurement of gravity's acceleration. So time squared. Let's say I put a -20 plus 12 here. So this would say, hey, here's half of my acceleration due to gravity. Here's a -20, should be times time. So this -20 would be -20 meters per second. Negative would indicate that the object that was thrown or launched was launched towards the ground. This +30 over here would indicate that the object was launched upwards or thrown upwards. And this 12 would represent 12 meters, or the initial height. So this is a typical setup for modeling vertical or projectile motion using a quadratic model. So here's something that's common. You'll be given information about the model. Hey, suppose that a ball is tossed upwards from the bottom of a 50 feet deep ravine from an initial height of 4 feet with an initial velocity of 64 feet per second. So there's some information that I gleaned from this. Initial height, that's my h naught. That naught or 0, h sub 0 represents time equal to 0. Initial height of 4 feet. And velocity, an initial velocity, that's v naught. Velocity at time 0, or v naught, is equal to 64 feet per second. That's horrible, isn't it? Feet per second. And I see that I'm measuring things in feet, which tells me that my acceleration is going to be negative 32 feet per second squared. So I know to use the negative 32 because I see that my other measurements are in feet, not in meters. And it's simply a matter of setting your model up. Height as a function of time equals 1/2 acceleration times time squared plus initial velocity v naught times t plus h naught. And you just plug your numbers into your model where they go. H of t equals 1/2 of a is 1/2 of negative 32 is our negative 16 t squared plus initial velocity is 64, so plus 64t plus h naught, initial height of 4 feet. And there you have the model. I went ahead and graphed this model. So here's the graph of it, and you can see that it has some key features on it. It has a height intercept right here. That's going to be the initial height of the ball, so that should be at 4. There's going to be a vertex, which will represent the highest point that the ball was tossed if it were thrown upwards. If we have a situation where we initially throw something downwards, we're not going to get a vertex on the model like we do here. But if we get an upward thrown object, we're always going to have the vertex representing the highest point that the ball traveled. We've got a t-intercept here, and this t-intercept right here represents when the ball is on the ground, when it falls back to the bottom of the ravine. And this t-intercept has time as negative. This is the time axis, time and height. Height as a function of inputs are time. This negative time here, this is a garbage intercept, so I don't really have any reason to calculate it. Negative time represents a moment in time before I actually threw the ball. So once we get the model set up, we can do things with it. So here on this screen, to help us remember what the model was, I went ahead and wrote it in where this graph is at. So it says find as an ordered pair, including units, and interpret the h-intercept. So remember, the h-intercept is just where we cross the h-axis, and that's going to correspond to time equaling 0. So to find the h-intercept, I merely plugged time equal to 0 into my model. My model's right here, so we'll get negative 16 times time squared plus 64 times time plus 4, and we're doing this at time equal to 0. So we're going to get 0 plus 4 equals 4 feet. As an ordered pair means put it into ordered pair form, including units means put the unit of measurement on each number. So this ordered pair here was input 0, output 4, but we need to include units. So it's 0 seconds corresponds to a height of 4 feet. And then it says interpret the intercept. So now it means we need to say something about it. So the interpretation of the intercept is simply that the ball was thrown from an initial height of 4 feet. There's my interpretation. So we found and interpreted that intercept. Now we can do something else with the model. It says determine when the ball will be at the height of the canyon wall. We were told that we were throwing the ball upwards from the bottom of a 50-foot ravine. So to get to the height of the canyon wall or the ravine wall, we'll need to get to a height of 50 feet. So here's my 50 feet mark, and if I draw the line through the quadratic model, I see that I get 2 intersections. There will be 2 times when the ball was at a height of 50 feet. Once on the way up, and over here on the way down. And we can get estimates for what time ought to be. We can kind of pull a line down and say, hey, that's at about the 1 second mark. And this looks like it's just a little over 3 seconds. So there's a graphical check on our work when we get done. So determine when the ball will be at the height of the canyon wall. So remember, we have a height model. Height is a function of time equals negative 16t squared plus 64t plus 4. And we're to be at the height of the canyon wall, h needs to be 50. The height needs to be 50 or 50 feet. So I replace the h, or the height, in the model with 50. We go 50 equals negative 16t squared plus 64t plus 4. And one way that we can solve this is just a quadratic equation in one variable. One way that we can solve this, based on work that we've done earlier this year, is to get this equation equal to 0 and use the quadratic formula. So I'm going to go ahead and use the quadratic formula this time. I'm going to subtract this 50 from both sides. So I'm going to get 0 equals negative 16t squared plus 64t plus 4 minus 50 is going to be a minus 46. So I'll get a minus 46 right here. And before we solve this, right, the quadratic formula, we're going to need to know a, b, and c, but we want to recognize there's a common factor. 2 will go into 46, 2 will go into 64, 2 will go into negative 16. Let's divide everything by 2 so that we reduce the size of the coefficients that we're having to work with. So we'll get 0 equals negative 8t squared plus 2 goes into 64 22 times minus 2 goes into 46 23 times. So now we have smaller numbers to work with in the quadratic formula. We can see that a is going to be negative 8, b is going to be 22, and c is going to be negative 23. So usually the quadratic formula is x equals, but now we don't have an x. It's going to be t is equal to, and we know it's the opposite of b, plus or minus the square root of b squared, minus 4ac, everything over 2 times a. So we just take the numbers we found here and feed them into the formula. So we get time equals the opposite of b is going to be negative 22, plus or minus, whoop, that's not a 22. 2 goes into 64 32 times. You have to do your math correctly, or you'll get junk. Garbage in, garbage out, right? So that's a plus 32. 64 divided by 2 is 32, not 22. So the b actually needs to be 32, which is going to make this, the opposite of b is going to be negative 32, plus or minus the square root of b squared minus 4 times a. A is equal to negative 8 times c. C is equal to negative 23. So we get the square root of this whole mess. And it's all over 2 times a. And a is equal to negative 8. So equals. And we need to simplify the stuff under the radical sign down. So we're going to get negative 32 plus or minus the square root. The square root of the stuff underneath the radical simplifies to 298. And work that out ahead of time. And this is going to be all over a negative 16. All over negative 16. And then we're going to crunch this number down and get some estimates for it. So if we do the math here, negative 32 plus the square root of 298 divided by the negative 16, and negative 32 minus the square root of 298 all over the negative 16, we're going to get time is equal to 0.98 seconds or 3.08 seconds, coming out of simplifying this expression right here. And then you want to eyeball the graph. Does it look reasonable? Yes, it looks like a height of 50 feet corresponds to about 1 second. That's about 1 second. It looks like a height of 50 feet also corresponded to about 3 seconds. That number's really close to 3 seconds. So those look good. The ball was at the height of the canyon wall at 0.98 seconds into its flight, and it was there again on the way down 3.08 seconds into its flight. Okay, so next it says find as an ordered pair, including units, and interpret the vertex of the model. And what we want to identify is that the vertex of the model is representing the highest point the ball gets. It doesn't get any higher than the vertex. And it looks like we're above 65 here for height, so that's kind of a check on work. We're trying to get the ordered pair that goes right there, but we want to include units. So remember that the vertex, the x-coordinate, or in this case we have time on this axis, the time coordinate of the vertex is given by the first part of the quadratic equation, right? The quadratic equation was x equals the opposite of b plus or minus the square root of b squared minus 4ac all over twice a, and this negative b over twice a gives us the x-coordinate or input coordinate of the vertex. In this case, we don't have x, we have t for time as our input variable. So we want to identify t equals negative b over 2a, and we know from our equation that a is equal to negative 16 and b is equal to 64. And we can go ahead and plug those numbers into this expression right here. So the opposite of b divided by 2 times a simplifies to negative 64 over negative 32, which simplifies to 2 seconds. So the input here is 2. Now I need to know the output, so I'm going to plug 2 into my height model. This is time. That's the time that corresponds to the vertex. Now we need the height at the 2-second mark, which is going to be negative 16 times t squared plus 64 times t plus 4. It's just using our model. Plug in time equal to 2. Crunch these numbers. We get negative 16 times 4 plus 128 plus a 4, and this is going to be negative 64 plus 128 plus 4 equals, that's going to be what, 64 plus 4 equals 68. So the other ordered pair is 68, but we are supposed to find it as an ordered pair including units. So if we're including units, we're saying 2 seconds into the flight the ball was at a height of 68 feet, and then it says interpret that. So the interpretation is the ball was at its maximum height of 68 feet 2 seconds after it was thrown. So there's our interpretation of that. 5. Find as ordered pairs, including units, the t-intercepts. And again, there's 2 t-intercepts. There's a time axis intercept here and a time axis intercept here. But we recognize that negative time over here is garbage, so we're just going to worry about finding the one that makes sense in the context of the model. And what we want to recognize is as we cross the t-axis, the height is 0. The height is 0 at the t-intercepts. So to find those, we have to replace height in the height model with a 0. So we get 0 equals negative 16t squared plus 64t plus 4. And now I have choices. I can solve this either using the quadratic formula, or I can complete the square. I'm going to choose to complete the square this time. So to complete the square, we know that the coefficient on the leading term t squared needs to be a 1, so I'm going to divide everything by negative 16, by negative 16, by negative 16, by negative 16, and then simplify. So 0 equals 1 t squared. We're dividing by a negative, so we're going to get a minus. 16 goes into 64 4 times. A negative being divided in, so we're going to get a minus, and 4/16 simplifies to 1/4. Now I'm going to get these two guys by themselves by getting the constant term over onto the other side by adding 1/4 to both sides, which is going to give me a 4th over here, equaling t squared minus 4t. Again, we're going to take the middle coefficient, the negative 4, we're going to divide it by 2, and we're going to square it, which is going to give us a negative 2 being squared, which is a 4. So I'm going to add this 4 to both sides to complete the square. I then recognize I've completed the square. Whose square did I complete? I completed the square t. Who got squared? Minus 2 got squared. To add these, I'll need a common denominator, so we're going to multiply this by 4 over 4. So we get 4 times 4 is 16, plus 1 is 17 over 4. We're going to take the square root of both sides. And typically when we take the square root of both sides, we go plus or minus here. But this time we can identify that this negative is going to wind up corresponding to this negative t value that doesn't make sense in the problem context. So I actually don't need the negative this time. We take the square root of both sides. The square root cancels the squaring. We get a t minus 2 equaling the square root of 17, which I don't know, over the square root of 4 is 2. And now I can add 2 to both sides to get the t by itself. So square root of 17 over 2 plus 2. And I worked this out ahead of time. I did square root of 17 divided by 2 plus 2, and I got t equal to 4.06 seconds. Actually, it's not equal to. That's wrong. I approximated this. I had to round it. The square root of 17 wasn't a rational number, so I had to approximate it with a rational number. So it says find it as an ordered pair. 4.06, but I'm also told to include units, so that's 4.06 seconds corresponds to my being on the ground or at 0 feet. So my interpretation is the ball hit the bottom of the ravine. It landed, in other words, 4.0 seconds after being thrown. So there's my interpretation. And we're going to do one last thing with this model. We're going to identify a contextual domain for the model. Contextual domain. And let's, while we're at it, get the contextual range. And we found a vertex. We found the vertex here at 268. We found a t-intercept over here. That t-intercept was at 4.06, 0. And we also found a y-intercept, or a height intercept actually, over here at input 0, output 4. So the h-intercept, we had found that as well. It was at 0 seconds, 4 feet. And the intercepts in this particular case give us everything that we need to do to establish a domain and range for the model. Remember, domain values are the inputs. Domains are inputs, or our t values are our input values, and we can look at these intercepts and kind of identify what's going on. Time is an element of what interval? Well, the ball is thrown at the 0 second mark, and it hits the ground at the 4.06 second mark. 4.06 So there's my domain and my range. The range is where the heights go. So the heights are going over an interval. Well, the lowest it ever gets is on the ground at 0 feet, and the highest we ever get is 68 feet. So there's a contextual domain and range for this model.